The relationship between mean kinetic energy and the temperature of gases is very straightforward, and we need to be able to derive this particular formula. Although this formula is given to you, the derivation is worth knowing. So we need to start off with a few equations that we already know. Number one is we know that PV is equal to a third of nmc squared, okay? And PV is also equal to nkt. Now, a couple of things that you already know. P is the pressure, okay, in pascals. V is the volume in meters cube. N is the number of particles contained, gas particles. M is the mass. And this is the root mean square speed, all right? And then we have the K, which is the Boltzmann constant, and T is the temperature in kelvins. Now, because these two are equal to one another, all right, we can say that a third of nmc squared is equal to nkt, and the number of particles cancels out, which gives you a third of mc squared with a bar equals k times t. Now, from here, we want to obtain a relationship between the kinetic energy and the kT, or the temperature, because k is a constant. Let me just write that down. It's Boltzmann constant, okay? And it has a value which is given to you in the exam, and it is 1.38 times 10 to the power of minus 23 joules per Kelvin. Righty, so from here now, we need to obtain or bring in kinetic energy, okay? Now we know that kinetic energy is half mv squared, or in other words, if I just use, so 1/3 mc squared can be written as 2/3 times pi 1/2 mc squared k times t. Now, all I've just done is broken this at like 1/3 into 2/3 times a half, because I want to introduce this ek, all right? So 2/3 times pi now ek is equal to k times t, which means that ek is equal to 3/2 kt. In other words, I've got my expression that I was trying to prove, and that also refers to the fact that ek is proportional, directly proportional to the temperature, because k is a constant and obviously 1.5 is a fixed number as well. So this is your relationship between kinetic energy and the temperature of the gas particles in kelvins. Now, over here, I've got a spring mass system of a glider. Okay, so this is a glider and it's basically being displaced. Now, on a horizontal track. Okay, so when it's displaced, it will exhibit simple harmonic motion, and it has two different forms of energy. The first one is the elastic potential energy, EP, and that is half kx squared, and where k is the spring constant and x is the extension. And the other energy that this system has is the kinetic energy of the spring and the glider. Okay, so ek. And that's also half mv squared. I'm just going to write that down. Okay, so I'm combining the spring and the glider together and assume that this is one single system. Okay, there's no friction present. So therefore the displacement x of the glider is the same as the extension or the compression of the string. Okay, so we know that because EP is proportional to x squared, it would be a parabolic graph. Okay, so parabolic function. And so is EK versus V graph as well. Okay, so we'll explore that in a second, but first let's just understand what happens to the energy when it's moving from a displacement of nothing. So it's moving from its resting position, x as 0, okay, from the center when it's resting. So we know that EP is also going to be 0. Okay, so this is at equilibrium position. And when it's moving all the way to a displacement, the maximum displacement, okay, so that maximum displacement is the amplitude A, that will give me EP as half Ka squared. Okay, so it varies from 0 to half Ka squared. Okay, I hope that makes sense. All right, now when the glider is at the amplitude or the maximum displacement, okay, when x equals a, then the glider will be stationary for a second, okay, so v is going to be 0, okay. That means that it has no kinetic energy, Ek will also be 0, therefore, and so the total energy of the system is going to be equal to half Ka squared. Okay, that's the total energy of the oscillator, okay, and the kinetic energy of the glider at any instant must therefore be the difference between the total versus the potential. Okay, so Ek equals E total minus Ep, okay, and that will basically mathematically be written as half Ka squared minus half Kx squared, okay, where x is the displacement of the glider and a is the amplitude. So we can just say that it's half Ka squared minus x squared, and that is your equation of kinetic energy of a system in simple harmonic motion that has potential energy in the form of elasticity, okay, it's a spring, okay, and so if you were to draw a graph of these two energies, so let's say you are drawing the kinetic energy graph, then we know, so let's have the displacement on the x-axis and the energy on the y-axis, then the energy, the kinetic energy, will vary from maximum at the resting position to 0 at the maximum amplitude, A, okay, and that would be symmetrical to the other side where it's basically compressing, okay, so it is an upside down U graph where the amplitude as it basically goes from 0 to A, the kinetic energy decreases, and similarly, the potential energy of the system would increase, okay, it would go from 0 at its resting position to a maximum at the maximum amplitude, okay, and the other side will be again symmetrical, so that's how it will look like, okay, so these 2 points match up. I know it's not quite clear from the graph, but this graph is for Ep and this one is for Ek, okay, and the total energy of this system is going to remain constant, and therefore it could be given as the sum of the two, like this. It'll be a straight line, and this is the total energy. So this is your equation of kinetic energy in terms of the amplitude and displacement, and that's the very useful graph for you to remember. Now, the planetary orbits can be modelled as circles for simplicity reasons, and Kepler's third law suggests that the square of the orbital period, t, of a planet is directly proportional to the cube of its average distance r from the Sun. So, basically, t squared is directly proportional to r cubed, and this is a relationship we are going to prove based on the information about the forces that we have about a planetary / circular motion. Okay, so we have our planet which is moving with a velocity v, okay, and in a circular motion, and it has mass m, and it is going to be attracted towards the Sun, and that's just the force of gravity. As we know, that is equal to gmm over r squared, where g is the gravitational constant, m is a mass, the capital M is a mass of the Sun, the lowercase mass is the mass of the planet, and r is the distance between the two. And we also know that as this planet is moving in a circular motion, it will have centripetal force as well towards the center. Okay, so F, I'm just going to call it Fc. And that force is given to us by mv squared over r. So in order for the planet to go in circular motion and be attracted to the Sun, these two forces are equal to one another. So we can say that gmm over r squared is equal to mv squared over r. And we can tidy this up quite a bit by multiplying both the sides by r and dividing both the sides by m. So we get v squared is equal to gm over r. Now this, we're halfway through actually, because we now need to relate or convert this velocity in terms of the time period. And we know that v is equal to 2 pi r over t. And we can use that in our equation here and square everything that we have. And further simplifying this, we'll make it into 4 pi squared r squared over t squared equals gm over r. Now, I need to make t squared the subject, and so if I just multiply both the sides by t squared, I would end up getting t squared and then gm over r equals 4 pi squared r squared. Multiplying both the sides by r will give me t squared, and also at the same time I'm going to divide both the sides by gm. So 4 pi squared over gm times pi r cubed. Okay, so this is our proportionality constant for a particular star, such as our sun. So this is a proof of Kepler's third law, which often comes up in the exam, so it's worth remembering. And further to this, you could be asked a question about a t squared versus r cubed graph. And we know that these are linear, the relationship is linear, so it will be a straight line passing through the origin, where the gradient of this graph is going to be equal to 4 pi squared over gm. Okay, so you can work out the mass of the sun or the star involved in a question. Okay, so please make sure you practice this derivation, as it has come up quite a few times in the exam. This formula is given to you, so you don't have to worry about remembering it though. Talk about a mathematical derivation of escape velocity. And if you have an object on the surface of the Earth, or any planet for that matter, and it needs to be lifted off, okay? Now, in order for it to be lifted off, energy must be supplied, and it would have to equal to the gain in the gravitational potential energy needed for this lift out of this particular planet's field, gravitational field. So if we can say that you are lifting off a mass m, you need to supply it with some kinetic energy, okay? And the kinetic energy supplied will transfer into gravitational potential energy of this particular object. And that is equal to gmm over r, where capital M is the mass of the planet, m is the mass of the satellite or the object, such as a rocket that you're trying to lift off, and that will be equal to kinetic energy, which is half mv squared. Okay, so if we just cancel out the obvious m's, we will get v as square root of simply 2gm over r. So no matter what the mass of that object that we're trying to lift off is, what matters is the mass of the actual planet, okay, because the field, the gravitational field, is created due to that planet, okay, and the distance r, which is obviously at the surface over here, but it could be any distance, you know, between the planet and the object, okay, so r is just the distance between the two. Alright, so this is a really simple derivation. It comes up in the exam for like a mark or two, so it's worth checking it out. Also, this formula is not given to you in the exam, so please do learn it. Alright, so yeah, happy days. Let's talk about the electric field between two parallel plates, like so. Now, we have a charge, small test positive charge, which is placed in between the two plates, and it will experience a force towards the negative plate, and therefore move towards it. So, if it moves towards that plate over here with a force F, then work is being done. Okay, so work is done as force times distance. And we also know that work is written as V times Q, as a potential difference is applied across the two plates over here. So if we put these two together, we will have V times Q equals F times D. And we know that the electric force on a charged particle is given to you by E times Q, where E is the electric field strength, which is a vector quantity, and Q is the charge on the particle. So we can safely say that VQ is equal to EQ times by D. And if you divide both the sides by Q, then you're left with V equals ED, or E is equal to V divided by D. And that's the proof of the electric field strength, which is equal to the voltage or the potential difference divided by the distance that the charge moves. So we can also say that because electric field strength is measured in newtons per coulomb, we can say that 1 Newton per coulomb is equivalent to 1 volt per meter. Okay, so those are the equivalent units worth remembering. Now, let's talk about the charged particles moving at right angles in an electric field. So you have a test positive charge Q, which is entering the electric field, and it's basically got a velocity V. And its motion can basically be affected by this electric field. And you can predict this motion in this electric field by analyzing its vertical and the horizontal components of the motion. So let's talk about the horizontal component first. And horizontally, we know that there is no acceleration. Okay, so no acceleration implies that the final velocity VH, okay, the final horizontal component of the velocity V, okay, VH, is going to be the same as the initial velocity that it started with, it entered the field with. All right, and secondly, we know that if the length of this electric field is L, then the time spent in this electric field can be given by T equals L over V. All right, so V is the velocity with which it's traveling. So that's the horizontal motion, quite straightforward. But when we talk about the vertical motion, we need to understand that there is going to be acceleration. Okay, and the acceleration could be given by A equals F over m, where m is the mass of this charged particle. Now we know that in an electric field, F is equal to EQ over m, okay? And secondly, we know that the initial velocity vertically, okay, so if I just say U, V, okay, where this bit represents the vertical component, just to be clear, okay, is 0, because it was traveling horizontally and not vertically. Okay, so that's 0. So if we want to get an expression for the final vertical velocity, okay, VV, which could be given by U plus A times T. Okay, so just to be clear, that's also the vertical velocity. So we know that this is 0, and this is EQ over m, okay, and T is, well, L over V, okay, where V is the initial velocity. Okay, so here you will have V equals EQL over mv. Now, you do not have to remember this equation at all. However, just be familiar with how to derive this, because it can come in many different forms, if not this particular one. Okay, so I hope you found this useful. Let's talk about the moving charges in a magnetic field. Now, over here I've got a magnetic field which is into the plane of paper, and let's take one charge which is moving from left to right. Now, according to Fleming's left-hand rule, we know that if the charge is moving from left to right and the magnetic field is acting into the plane of paper, then the force experienced by this charge will be upwards. Okay, so let's put that down over here. Force is upwards. And this magnetic force can be written as F equals BIL, where it is acting perpendicular to the magnetic field. So we know that if this charge is moving a certain distance, let's call it L, then we can also rewrite L as v times t. Okay, so it is just in terms of the velocity times by the time that it takes to move that certain distance. And we also know that I is equal to q over t. So if I just say that, let's say that F is equal to b times by q over t, okay, times v times t, then the t's cancel out and it gives you force acting on this charged particle, this moving charged particle, as bqv, where the letters have their usual meanings. F is the magnetic force in newtons, b is the magnetic flux density, which is in Tesla, q is the charge in coulombs, and v is the velocity in meters per second. So this could be also applied to an electron. Okay, F equals BeV. Okay, so although this formula is given to you, it's worth knowing how to prove it. Now, if you were to consider another case, or the same case but slightly in more detail, so let's say this charged particle is moving, okay, but because the force is acting upwards, it's basically going to go in a circular path. Okay, the force is acting on this particle, it's always perpendicular to the velocity. Okay, so we can link this to the centripetal force. Okay, and from circular motion chapter you would remember that the centripetal force is mv squared over r. So where r is the radius of that circular path, m is the mass of that charged particle, okay, and v is the velocity. So if we link this formula to the one that we've just proven, so that is if the two forces were equal, okay, bqv is equal to mv squared over r. So we can get a lot of relationships over here. We can firstly rewrite to cancel one of the v's. Okay, and we can say that r is equal to mv over bq. So we can safely say from here that r, or the radius of the circular path, is directly proportional to the velocity and the mass, okay, but inversely proportional to the magnetic flux density and the charge. So those are some of the relationships that you can derive if you know this particular relationship, which is not given to you in the exam. So it's worth remembering it, or at least knowing how to get it, basically. Hope this helps.